right, we have been through 3 days or so of data acquisition. There's a few things that I want to cover just to do a recap. And the first one is this, and that is that data acquisition is obviously a potential source of serious, hard to recognize errors. And they come from three sources. The transducer and measurement errors, which are the subject of other courses, analog errors, noise, nonlinearity. These are due to poor design, inadequate common mode rejection, poor cabling and grounding. Then we've learned that when we use anti-alias filters, which are a requirement, they are going to distort the data. And that's an error if we don't recognize it. And then the most important one is sampling and discretization errors. Inadequate alias protection is the big bugaboo that we've been harping on for the whole course. And then inadequate resolution. That's not much of a problem anymore because most of the data acquisition systems that we're using today have plenty of resolution. The course has concentrated on the pitfalls of data acquisition, and you may or may not have them, but one of the things you do have to do, as we're going to see shortly, is to prove that you aren't subject to some of these problems. But what we've done is we've tried to encourage consideration of the things that might corrupt the data. And of course, the full message is that by doing it right, the errors incurred by the data acquisition system will be the smallest part of the overall experimental error. All right. Okay, aliasing errors. We've seen that it is impossible to have zero aliasing errors, but some part of the frequency range between 0 and the Nyquist frequency is acceptably aliased. And part of our experiment design is to determine what that is and determine what our actual bandwidth is that we can test over. Data between 0 and the F sub D, desired frequency range, is acceptable. Data above that frequency range is not acceptable as errors that are too much for us to accept. Amplifiers and cabling. This is one of the places where a lot of data acquisition systems fall short. If we're measuring small signals, such as from thermocouples or strain gauges, we need to use good amplifiers with good common mode rejection if we're expecting to get decent results. And decent results mean using the full dynamic range of our data acquisition system. We've seen that a good data acquisition system can have more than 90 dB of dynamic range. If we haven't done our instrumentation and wiring properly, we can't even approach that. We've seen that when we do use anti-alias filters, which most of the time we have to, unless our experiment limits the bandwidth by itself, we have to have anti-alias filters. In most applications, the low-pass filters are required. The distortion caused by these filters is normally ignored, but as we've seen, if we have two different data acquisition systems, perhaps one with a sigma delta system and one with a Butterworth or Bessel filter characteristic, the results can be different by up to 50%. And this is an error, if you don't recognize it, definitely should not be ignored. And one of the things I've shown you in this class is that we can do correction of the data so that the data will look like another data acquisition system, another anti-alias filter characteristic. But one of the faults of digital data acquisition or any data acquisition system is that we really can't measure the absolute truth. We can measure a consistent and reproducible representation of the data, but we can't represent the truth because of the distortions that are caused by our data acquisition system. Big question is, you have now, or soon will have, a digital data acquisition system. Otherwise, you wouldn't be here. The big question is does it or will it do what you need? And going back to one of the first slides that we showed you on the first day is don't trust anybody. As we said then, the first one you shouldn't distrust is yourself, but then the next one you should distrust is your data acquisition system or instrumentation system supplier or the person who bought the system before you came along. And the fundamental problem is that vendors will lie to you, or maybe they simply don't know, and so they're going to sell you a system that will make money for them, but it may or may not be a system that will do what you want it to. So when you're looking at the system that you have or looking at a system that you might potentially buy, things to watch out for are systems or devices with no accuracy specifications. If there aren't any accuracy specifications, then you can rest assured that the data acquisition system vendor or builder hasn't characterized their systems properly, and so there's no way that they can tell you how accurate the systems are. And then when we were looking at system specs, the question is whether the system accuracy specifications are reasonable. And if you get something that says an accuracy of about 1%, that's very suspicious. Now, maybe 1% reproducibility from test to test is good, but 1% accuracy is something that real systems really can't attain. So anyway, the only way to make sure a system will do what you want to do is test it yourself. And in the last chapter, the previous chapter, we showed that a set of relatively simple tests that separate the garbage from the good candidates. And in general, those tests that we talked about earlier are enough to determine whether the system is adequate for doing what you want to do. When you're buying a new system, ask for references. Ask the vendor to give you references for users that they have sold systems to, and then of course you should check them, call them. And a message there is don't call the manager, call the peon that actually uses the system. The manager will say the system is wonderful because his bonus depends on that. The peons will be a whole lot more honest with you. The other new tool that we've got now is LinkedIn and other forums that you can go out and ask questions. If you've got a system that you're buying or that you already have in hand, you can check on the web to see what other people's experience it is. If you've already got the system in hand, what happens if it fails the tests in Chapter 14? I've had several instances of students who have gone back to their laboratories, tested their data acquisition systems, found that they fail, found that they're not adequately alias protected. If they fail, you've got a serious political problem. Is the previously acquired data bad? How bad is it? What do you tell your customer? And a year or so ago, I had a very good example of this where one of the students went back to their lab, found out that their data that had been acquired for the past 5 years was completely corrupt, and he was a strong enough political guy to get everything changed and honest enough to tell the people that had data that they'd acquired that their data was no good, and a lot of it was redone from there. If your system is no good, you have got to be honest about it. You've got to play the political game. Okay, where are we headed in the future? Sigma delta converters are the most important breakthrough that we've had in the last 25 years. And in fact, there haven't been any other major breakthroughs since then. And for folks working in the audio frequency range up to 100 kilohertz or 200 kilohertz, sigma delta converters are going to be used in almost all of those applications. The only place where they can't be used is when their inherent delays is a problem. Significant, expensive, big analog anti-alias filters will slowly disappear. 16 bits will become the standard required resolution. As we've said, there are plenty of systems out there that have 24 bits. The question is whether it's worth using those. Modern systems and systems that are probably going to be available in the near future are going to have 15, a little over 15 effective bits of accuracy for the entire system, including amplifiers, wiring, and everything else. PC clones and their offspring will be the computer of choice, but pads are becoming important, particularly if you've got a portable data acquisition system. And some of the software and hardware vendors are supporting iPads and Android pads and that sort of thing. Don't see any radically new system architectures on the horizon. Improvements are going to be in cost, size, and ease of use. Most important thing is, though, is the data acquisition process is only a cog in a much larger testing program. It's critical that the data acquirer be a full and cognizant member of the team. That's the only arrangement that can produce good results. And of course, the thing that the acquirer is responsible for is to make sure that the data is good, is a good representation of what's actually going on in the experiment. And so the acquirer is going to be responsible for selecting the transducers, cabling, signal conditioning, and then analysis of the data to the point that it can be assured that it's valid. And you need to assure that the data is adequately alias protected, that it's out of the soup, and that the data actually makes some sense. So, thank you for participating in the in TTI 196. I will be happy to entertain questions, and hope to see you sometime soon.